Good morning, friends. It's time to begin the class. A couple of announcements. So, reminder: next class will happen day after tomorrow, which is October 16, Saturday. Usual class timing. This is a buffer day as per the institute calendar. The next quiz, I'm planning to have it sometime in this around October 28 to October 31. Okay, we'll finalize that depending on the TA's availability. And this is for you to plan your onboarding accordingly. So don't plan to come on that weekend. Although I don't expect too many people to come on that weekend, because on the following weekend you have Diwali. So fine. So that should be okay, I hope. All right. So what did we do in the last class? Let's do a quick recap of all that, because I thought we did a lot of things, right? Okay, so we defined what do we mean by a reflexive relation, a symmetric relation, an antisymmetric relation, a transitive relation, and so on. And then we said that we say a relation is an equivalence relation if it is reflexive, symmetric, and transitive, right? So what was the motivation behind studying these kind of relations? It was like, so it captures the notion of similarity, right? So if everything is similar to itself, if something is similar to some other thing, then that other thing is similar to the first thing. If A is similar to B is similar to C, then A is also similar to C. Also, basically, all this is captured in the notion of an equivalence relation. Shrivanti, October 30, 10 to 11 a.m. We have called 215 quiz. Okay. Okay. So. Let's do it this way. I'm pretty sure I'm going to forget this after this lecture is over, unfortunately. So once I declare a quiz, let me know if it conflicts with whatever all other commitments that you have, academic commitments that you have during that period. Okay, but yeah, good that you let me know, or maybe let me just note it somewhere on the slide so that I'll remember. Hopefully. So what is it? October 30, 10 to 11. You have called 215, please. Okay. Fine. Sounds good. All right. Yeah. And then we said that, right, the counterpart of the notion of equivalence relation is something called a partition of a set, right? What is a partition of a set? It is just a way of splitting the set into several subsets, right? So formally, so it's a collection of subsets of S such that no set in that collection is empty. Uh, the collection covers all elements of S, right? So every element of S is in some set in the collection P, and finally the sets in the collection P are disjoint. So basically, every element is covered by exactly one set in P, right? And then we said that there is a natural correspondence between equivalence relations on the set S and partitions of a set S. So one way it was easy, given a partition of a set S, there is a natural equivalence relation associated with it, which is we say two elements X and Y are related uh, if they belong to the same set under the partition. And then we ask the other side of the equivalence. So given an equivalence relation R, does there exist a partition P which induces R, right? So can we invert this correspondence? And then for that we defined the notion of an equivalence class of an element X. So how did we define it? So if R is an equivalence relation on a set S and X is an element of S, we denote by X within square brackets with a subscript R the set of elements Y which are related to X under R. Okay, which is so this is the set Y in S such that XY is in R, which is also due to symmetry property of the equivalence relation. This is also same as the set Y in S such that Yx is in R, and this is called the equivalence class of R. And then we saw that if R is an equivalence relation, then the set of all equivalence classes, okay, So for every element, you construct the equivalence class, put it in this collection of sets, right? And then you remove all the duplicates, right? So because I mean, this by definition, because this is a set after all, right? So this forms a partition of the set S, right? So I hope you all remember this. One notation that I forgot to introduce in the last class is the following. So notation, right? So if R is an equivalence relation on S, then this set, right? The set of all equivalence classes of R, so we'll denote it by S divided by R. Right? So if you go back to the example that we took last time, right? So we were trying to define this set of rational numbers, and then we just said that well, taking Z cross, we started out with the set Z cross Z minus 0, or what did we start out with? Yeah, Z cross Z minus 0. Then we defined some equivalence relation on pairs, right? We said that AB is equivalent to the pair CD if AD is equal to BC, right? So we defined this equivalence relation, and then we said that the equivalence classes of this equivalence relation are nothing but the rational numbers. So formally, you could define the set of rational numbers as what? As this set Z minus Z cross Z cross Z minus 0, Z cross Z minus 0 by this equivalence relation. Okay, any questions so far? All right, cool. Okay, so then what else did we do in the last class? We introduced this idea of right. So given a set S and a relation R on S, right? So does it make sense to define some kind of a smallest equivalence relation that is superset of R? So then we said that okay, given a relation R on S, look at all possible equivalence relations on S that are supersets of R. Okay, so we defined the script R to be that class of equivalence relations, and then we said that if you take the intersection of all those relations in the script R, that actually first of all is an equivalence relation. That's easy to verify. Because each of these sets R prime is a superset of R, therefore their intersection is also going to be a superset of R, so that is clear. And then finally, for every equivalence relation which is a superset of R, well, that equivalence relation appears in this set script R. So therefore, this equivalence relation R star can only be smaller than that, can only be a subset of that. Okay, so therefore this object that we have over here is nothing but the smallest equivalence relation, which is a superset of R. Okay, so there is nothing specific to equivalence relations as far as this claim is concerned, right? So what I could have also written is, let R be the set of all. I mean, I could have replaced this equivalence by I could have very well replaced this equivalence relation, this word equivalence by reflexive, symmetric, transitive, what else? And correspondingly, I will replace this equivalence by the corresponding reflexive, symmetric, transitive. Right, so still the claim will hold. I think it's easy to verify. Yeah, 2 and 3 are straightforward. It's just a matter of verifying that the intersection of an arbitrary collection of reflexive relations is reflexive, Symmetric relations is symmetric, transitive relations is transitive, reflexive and transitive relations is reflexive and transitive, and so on. So it's easy to verify all this. Okay, so now what we are going to focus on this time, in this class, is how do you compute, right? So how do you compute this kind of a closure, right? So so first we need to define the notion of a closure of a relation, right? So let's do that. The transitive closure of a relation R on S, denoted by R plus, is the smallest relation on S which is transitive and is a superset of R, right? So the same idea, right? So that is R plus is the intersection of all R prime relation on R, of all R prime which is a transitive relation on R, transitive relation on the set S, and which is a superset of R prime. Right, and analogously you can analogously define the notion of a reflexive closure, symmetric closure, transitive closure we have already defined, reflexive transitive closure, reflexive symmetric transitive closure, and so on. Analogous. Okay, so now let us ask the question: how do you compute the transitive closure algorithmically? Question: given R, can we compute R plus algorithmically? Jagdish, are you saying something? I'm not able to hear you, but Teams is saying you are speaking something. Sorry, Rhythm. Okay, Vibhanshu, yes, your hand is up.
Sir, we will just add those ordered pairs which are essential. Essential in the sense, absence of those are making our relation non-transitive. We will add those ordered pairs to our relation.
Okay, sounds like a reasonable idea. How do you find all such pairs?
For example, AB is there, AB ordered pair is there, BC ordered pair is there. Then we will add AC.
Then you will add AC, and then how long do you continue? When do you stop?
I will continue till then, till our relation is non-transitive.
I see, I see. And as soon as you find that your relation becomes transitive, you'll stop.
Yes, sir. Yes, sir.
Okay, sounds reasonable. Abhinav?
Sir, I have a doubt.
Yeah.
Confused here. In the red claim that R star is equal to the intersection of R dash belonging to R dash. So here R dash is a subset of R, right? And that too we are taking intersection of R dash. So how can R star be a superset of R? I'm not getting this.
No. So wait, so you're talking about this expression?
Yes, sir. Here.
This expression you mean?
Here R dash is a subset of R, right? It belongs to R.
No, are you wait? So are you talking about this R star or R plus? Which expression are you talking about?
Sir,
I
R
mean,
star, R star.
R star. But how did we define the script R? Right. So it is the set of all equivalence relations on S that are supersets of R. Not all relations on S which are supersets of R.
Oh, okay, fine.
Right.
Yeah,
Okay.
okay.
Yeah, and similarly we did over here. Ramanuj?
Sir, I think a good analogy for transitive superset, like the transitive superset is,
Huh?
yeah, the transitive closure is that you take a directed graph and you completed all the directed cycles. So like if there is
directed cycles, what do you mean?
So like there is A to B and B to C,
Huh?
and then you have the cycle C to A. So it's a path, like it's a cycle. So every cycle like this is completed directly.
So there is a fundamental problem over here, Ramanuj, because let's say A, right? So by a directed edge, you mean that A is related to B, right? So if A is related to B, then you're putting this directed edge, I suppose. Right, Ramanuj?
Yes.
Okay. So
Yes,
suppose A
yes.
is related to B and then B is related to C, right? So that does not imply that C should be related to A in the transitive closure. All that implies is A should be related to C in the transitive closure. So this is what we need to add.
Like the cycles should be in a opposite type way, so something like that, I think.
Well, so let's not even use the word cycles, right? So what we are really saying is, you're really asking the question: is C reachable from A? Right?
Okay, so if there is a path from A to C, then we add a
direct edge. Exactly. So if there is a path from some vertex to some other vertex, you'll just shortcut it and add another edge, direct edge. Yeah, that is a good analogy. Yes, Abhinav. Abhinav, your hand is up. Okay, Aniruddha.
Hello. So I had a doubt regarding the closure of basically a set. Does closure always need to be either transitive, reflexive, symmetric, or some combination of that, or can closure as a property be applied to in a more general sense? Just
it can be provided. It can be. So you could talk of. So let's say you have some relation R and then you have some property Q. What is the smallest? What is the smallest relation which is a superset of R and which also satisfies the property Q? You can say that provided this is guaranteed, right? So if you take the intersection of all the relations which are supersets of R and which satisfy Q, the intersection should guarantee to satisfy Q. Only then it makes sense.
Okay. So if that satisfies Q, then we can define a closure on the property Q. Okay.
Exactly. So this is a crucial property over here. R star is an equivalence relation, right? Okay. Yeah. Go on.
And one more doubt regarding the Ramanuj's idea. So the relation S can actually be countable, right, or countably infinite. And,
okay. S is some set.
So if S is countably infinite, then how would we proceed with the graph path idea? Because we define graphs only on finite.
Valid point. Very valid point. So basically, you're trying to say that this idea will work only if the set S is finite.
Yes.
Valid point. I agree. Valid point. And
or unless we kind of extend graphs to be infinite, which I think we can do maybe with some more work.
If you do that, Aniruddha, even if you do that, when you are talking about an algorithm, you want the algorithm to terminate eventually, right?
Correct. Okay.
Right. So suppose my set S is just the set 1, 2, 3, 4, and so on, and my relation R is just the set of pairs 1, 2, 2, 3, 3, 4, and so on, right? Now, if you run any algorithm, how are you ever going to terminate and correctly find the transitive closure of R? Right. So, what is the transitive closure of R in this case? Right. So, does somebody want to cleanly say what is R plus in this case? It is the set of all x, y such that.
y is equal to x plus 1.
Transitive closure.
X is less than y.
X is less than y. Yes, very nice. Right, so it's just going to be impossible for you to kind of get hold of this set using an algorithm in finite amount of time. Right, so in general, if you are trying to algorithmically do something, your input needs to be finite. Otherwise there is not much you can do. Okay, Arin.
No, sir, I got my doubt clear. The same as Aniruddha was asking for finite and infinite sets.
Okay. Yeah, so yes, so how can we compute R plus algorithmically? Assuming what do we need to assume? Let's just assume S is finite. I mean, I think it should be possible to do that even if R is finite and S is not finite, but let's just assume S is finite. S is finite implies R is also finite. Okay. Yeah, so I think somebody, Vibhanshu, suggested that, okay, you just keep on searching for pairs, you just keep on searching for triples ABC such that AB is in R, BC is in R, and AC is not in R, and then you just add the pair AC to R, right? So this is the idea that we'll use. But potentially, I mean, as just because the set S is finite, the set of relations, this set script R is also going to be finite. You could just find all the relations in script R by brute force and then take their intersection. So maybe that is the first obvious algorithm that I would come up with, at least. But we are really interested in an efficient algorithm, something more efficient, more smart than the brute force approach. Shrimanti?
So could you repeat once, how did you define R for that? S equal 1, 2, and then how did you define R?
Yeah, so in this example, you mean?
Yes, sir.
Yeah, R is just 1, 2, 2, 3, 3, 4, right? So R essentially, let me just redefine R. Right, so R is just the set x comma x plus 1 such that x is a natural number. That's it. Right, so S, which is the same as n. Right, so is it okay now, Shrimanti?
Yes, sir. So I read that 3, 2, so I couldn't understand how R plus was x less than 1.
Oh, I see. Okay. Vibhanshu?
Sir, in what way this diagram is helping us in this problem? I mean, what is why we introduced this diagram? What is the use of it?
What?
This diagram A, B, B, C, A, C.
Yeah, that just exactly tells you that it is the idea that you had, right?
It is just for imagination.
Yes. Yeah, if that helps you, just look at the diagram, otherwise ignore it. Doesn't matter. Yeah. Okay, so how do you compute R plus algorithmically? So the idea Vibhanshu gave is correct, and the algorithm we'll discuss is going to follow that idea, except that we will introduce some more notation to prove that the algorithm is correct. Shrimanti, your hand is still up, by the way. Okay. All right. Okay, so now definition. Let R be a relation on the set S and let n be a natural number. Okay, let me just make it n union 0. Okay, so for n greater than 0, define, right? So I'm going to define this relation, define the relation R to the power n on the same set S as follows. Right? How do we define R to the power n? R to the power n is the set of all xy in S cross S such that there exist elements z0, z1 up to zn in. So let me just write the definition and then we'll try to parse it. Z1 to Zn in S such that x is equal to Z0, Zn is equal to y, and for all I, Zi minus 1, Zi is in the relation R. Right? So if you, what does this mean? So if you just go back to the directed graph picture of a relation, right? So all this means is R to the n, right? So yeah, so R to the n is the set of all pairs xy for which there exists a length n directed path from x to y. Okay, and what is so, and moreover, R to the 0 is defined as, what is the natural notion that will come to your mind? R to the 0 is the set of all what? How should we define it? Okay, is the definition of R to the power n clear?
Reflexive relation.
Yeah, correct. But okay, my question is the definition of R to the power n clear? If not, just raise your hand as soon as immediately. Okay, yeah. So R to the power 0, Shrivanti suggests that, okay, we should define the, what do you mean by reflexive relation? There are tons of reflexive relations. Which one?
The smallest.
Smallest
Just
one.
only the.
Smallest one, yeah, makes sense. Okay, so R to the 0 is just defined as the relation xx such that x is in S. Okay, so now what? Now how do we write the right? So I didn't probably introduce a notation. Smallest. Okay, so let me just add this. The reflexive, symmetric, transitive closure of a relation R on S denoted by, we'll denote this R reflexive, symmetric, transitive closure of a relation by R star instead of R plus is the smallest relation S, which is reflexive, symmetric, and transitive, and is a superset of R. Right. So let me just add this little notation to this definition. Right. So now my question is, how can I write R star, R plus, and R star in terms of these relations, right? So observe R to the 1 is equal to R, right? So check that. So I want to write these relations R plus and R star in terms of the relations R to the 0, R to the 1, R to the 2, and so on. Can we easily write that? Let's worry about R plus first. Let's not worry about R star. Rishabh?
So could you repeat the question?
Yeah, so my question is the following. R plus is the transitive closure of the relation R. R star is the reflexive symmetric transitive closure of the relation R. How can we write these relations R plus and R star in terms of the relations? Okay, let's not worry about R star. Let's just do R plus for now. Okay. How can I write the relation R plus in terms of the relation R to the 0, r to the 1, r2, r squared, r cubed, and so on.
You
Okay.
do take the union of R1, R square up and so on.
That's it, right?
Yeah.
Cool. So let me state that as a theorem. Let R be a relation on a set S, then R plus is equal to R to the 1, which is equal to R. Right, so let me just write it as the union over all M in the set of natural numbers R to the power M. So how do you prove this? Yeah, Rishabh.
No, I don't have a complete proof.
Okay, I see. Is it okay? So the plan will follow is the following. So let's call this LHS and let's call this RHS. Left hand side, right hand side. We'll prove that left hand side is a subset of right hand side. Right hand side is a subset of left hand side. Right. So why is left hand side a subset of right hand side? Which one is the easier direction? Yeah, I guess right hand side subset of left hand side is the easier direction. Why is each r to the power m a subset of r plus? Right, so r to the 1 is a subset of r plus by definition, right? We want r to the 1 is just r, and r plus is a superset of r by definition. So therefore r plus is a superset of r to the 1. What about r to the r squared? Why should r plus be a superset of r squared? Is it so difficult? I mean, people seem to be lost.
Sir,
Yeah.
I'm unable to get it, sir.
Okay. Okay. So let's get back a bit. Is the definition of r to the power n clear?
No, sir.
Okay, it's not clear. It's not clear. Okay, fine. So let's get back to the definition of r to the power n. Right. So as somebody said, I don't remember who, we can represent a relation r by a directed graph. How? We could, right? So we put an edge from x to y. Oh wait. If and only if x is related to y. Right. So let me just plug up my computer. Okay. Now let us draw some relation. Okay, maybe x is related to x. Okay, I just constructed some arbitrary relation. Okay, there are some raised hands. Rishabh, yes?
Sir, I had a question here. When you're trying to prove this, we're defining R plus as the intersection of all greater transitive
Correct.
sets. Or okay.
Correct. Yeah, Arin?
So I think I got the answer.
You got the
At least
idea?
general, a general
Okay,
idea.
fine,
Yes.
fine. But let us go through it a bit slowly for the benefit of the class. Right. So now I just give you the relation r, but now what is r squared now? So if this is r, what is r squared? Where should I put edges? Right. So for instance, what? So is x related to y under r squared? Can I say that x r squared y over here? So if this is the relation r.
No.
No, sir.
Why?
Length two paths, na?
Yeah. So x y is a length 2 path, no? Right. X is related to x is related to y. right? So x is related to y under r squared. For instance, over here, x is related to z under r squared. What else? What other examples can we construct? So is z related to y under r squared? Can I say z is related to y under r squared?
No.
No.
Yes,
Yeah.
sir. Why? Yes,
Why?
sir. You can say.
How?
Okay, Z to Y. Y to Z is there.
Ha. Yeah, y to z, yes. So y is related to z under r squared. This is okay, but this is not the case.
No, sir, there is no h from y to y, right? So
Yeah.
how do we have a length two path?
Exactly. So which is why you will. So sorry.
So from y to z we'll get to length one path, right?
No, but y to z and then you go from z to
Oh,
z1.
okay, y z
Y Z
Oh,
Z.
Y z z exactly. Okay. Right. So now is it clear that r squared must be a subset of r plus?
Yes, sir.
Why?
So because it's a transitive function, so you have a to b and b to
Exactly.
c. So
Exactly. So what does transitivity imply? Transitivity implies, okay, just look at this part, right? So if you have x is equal to z0 and zn is equal to y, and you also have a sequence z0, z1, and so on up to zn, such that each zi minus 1 zi is in R, right? So all this will imply that xy is in R plus, right? So why? Because zi minus 1 zi belonging to R implies that zi minus 1 zi belongs to R plus also, right? And because R plus is a transitive relation, what does that tell me? So, well, Z0 is related to Z1, Z1 is related to Z2, so Z0 should be related to Z2. Z2 is related to Z3, so Z0 should be related to Z3, and so on. Right? So there is an inductive argument going on over here, but that inductive argument will tell me that Z0 should be related to Zn under R plus. Okay, is this absolutely clear? Is this absolutely clear? Should we wait for a couple of seconds? Maybe that is a good idea. Right? So although transitivity tells you if this is the case and this is the case, then this also is the case. Right? Although transitivity, as stated, just talks about three elements of the set. Well, by induction, it can be extended to this kind of a situation also, right? So if this is Z0, Z1, Z1 is related to Z2, Z2 is related to Z3, and so on, Z99 is related to Z100, all this will imply that Z0 is related to Z100. And in fact, Z0 is related to everybody over here. And each of these earlier Zi's is related to a later Zj. Right? So that is what transitivity is going to give you. Okay, so now let's get back to the proof of the theorem. Is it clear that right hand side is a subset of left hand side?
So when we say that given this relation Z0 related to Z1, so we are constructing R plus, right?
Yeah. So I'm talking about a transitive relation.
Okay.
Right. So I'm not talking about this specific R, which might not be transitive. I'm talking about any transitive relation, not just R plus. Okay. So now is it clear that RHS is a subset of LHS? Or in other words, is it clear that for every M, R to the power M is a subset of R plus? People still seem to be lost.
yes, sir, it's clear
Yes,
now.
sir,
It's
clear.
clear.
It's
Okay,
clear.
so raise your hand if it is clear. Raise your hand if it is clear that RHS is a subset of LHS, i.e. for all M in the set of natural numbers, R to the power M must be a subset of R plus. Okay, so there are a lot of raised hands. Others, you will have to speak up. What is the issue? So half the class, more than half the class has understood it almost. Is there any specific question from the other people? Okay. So I think we should move on, because I have, at this point, I have no idea what is the issue with the other people. Maybe they'll watch the lecture offline once again, and they should get back to me if something is not clear. Okay, yeah, so you could lower your hands now. Okay, so I'll just leave it by saying that prove this by induction on N. On M. Okay, so now what about the other way? What about LHS subset of RHS? Yeah, Arin?
Yes, sir. So we can say that what we have to prove is if an element belongs to R plus, then it should belong to at least one of the R raised to the power M.
Correct. Correct.
Yeah. So here we take any element that belongs to R plus. Now, if that belongs to R, then it should belong to R raised to the power M.
Yeah, sure.
Yeah.
It belongs to the RHS, you mean? Yes.
Yeah. And if it does not belong to R, let's just say AB, then there must exist two elements in R plus, AC and CB. Only that would be the case that AB would belong to R plus, or else it should not belong to R plus.
Why?
Sir, because R plus is the smallest
No, but
transitive.
again, you could have this kind of a situation, right? This is your XY.
Yeah, so I said belongs to R plus. I mean, just number this X, X1, X2, and Y. You could please number it. Yeah, so I said X1, X2 should belong to R plus. I did not say X2 belongs to R.
Sorry, so could you repeat your argument? I don't think I understood it then. So suppose XY is in R plus, then what happens?
Then there must exist two pairs, X, X1 and X1, Y, such that both belong to R plus.
So you mean to say there must exist some X1. So you mean to say either, okay, you mean to say XY is in R. Wait. XY is in R, or there exists some X1 such that X1 is in R plus and X1Y is in R plus.
Yes, sir.
Why is this so?
So this should be the case. Otherwise, XY won't belong to R plus.
That's not a concrete argument, Aryan. I mean,
I have a general idea.
Huh.
So why shouldn't be this case? So I mean, just intuitively, I'm saying.
Acha. So maybe what you should really say is, suppose we remove the pair XY from R plus. So okay, suppose this is the case, then you're done. Suppose this is not the case. Suppose XY is not in R. Suppose you remove XY from the set R plus. Right, so because R plus is the smallest equivalence relation, which is a superset of R, right? So by removing XY, you should get a relation which is not transitive.
Yep, that's same argument. Okay.
Right, and why is it not transitive? So, yeah, so basically, then there will exist some, exactly, something like this.
Yeah.
Okay.
I just said a general idea.
Sorry.
Yeah, and by doing this, we just reduce the size. Means we reduce the size from X to Y.
Okay, I see.
Okay. I mean, I don't have a concrete proof, but this should work. I think idea should work at least.
Yeah. Good. That sounds reasonable. Yeah, that is the idea basically, yes. Okay. So other way of proving this is the following. Ramanuj, yes, your hand is up.
So can't we just prove it that R union of R to the power m itself is a positive closure, and in R to the power m, like there does not exist any two relations such that x comma y and y comma z, and x comma z doesn't exist. So this doesn't exist in union R to the power m. Therefore, R to the power m is a transitive closure of R, and we're done here.
Yeah,
Because
that's exactly what I wanted to say. What you could other way of proving this is the following, right? So we will prove that this right hand side itself is a transitive relation. Okay, right? So right hand side is clearly a superset of R. Right hand side is a transitive relation. Left hand side is the smallest transitive relation, which is a superset of R. Right? So that will imply that left hand side is a subset of right hand side. Right? So we prove that the relation on the right hand side is transitive. Right? So recall that RHS is a superset of R, and LHS is the smallest transitive superset of R by definition. Right? So RHS is a superset of R. RHS is transitive. Let's say we proved it. Now LHS is the smallest transitive superset of R. So therefore LHS must be a subset of RHS. That's the plan. Right? So why is RHS a transitive relation?
So because we can just prove it here that if x comma y and y comma x exists and y comma z exists, then for example from x to y it is R1, and like y to z it's like for example there exists a path of length, you can say just m, from something to x to y, and then there will exist a path of length n plus m plus 1 from something to x plus y to z, and then this
Why
will
m
make
plus 1 specifically? There exists some path of length some m prime from y to z. Then what happens?
Then we we'll have a,
well, so that was not even a path, right? So this is just a walk, right? I never said that the zi's are distinct.
okay, so there exists a walk, then we can just connect
right?
x comma z. And
absolutely Vivanshu?
Sir, I was wanted to prove the same thing, that the right hand side is transitive. For example, I will prove it by contradiction, that if x and y are related in this union, and y and z are related in this union, then suppose x and z are not related, are not in this union. Then I will.
Okay.
For example, suppose x and y are the endpoints of a string of length n in the relation R of length n1, and y and z are the endpoints of a string of length n2 in the relation R.
Okay.
And because the RHS of union, RHS contains all strings of length, all in natural number, then x and z will be the endpoints of a string of length n1 plus n2.
So I think correct, Vivanshu. You are essentially saying the same idea. Yes. So let's write it down formally. Yeah.
Yes,
so I hope some of you have the idea already. Good. Right. So So how do you prove LHS is RHS? So suppose So how do you prove RHS is a transitive relation? So suppose some xy in RHS and yz is also in RHS. Right. So then what does that mean? So therefore there exists integers m1, m2 in there exists m1 natural numbers m1, m2 such that xy is in R to the m and yz R to the M1 and YZ is in R to the M2. Right, so that is just by the definition of union of sets. Right, so now what does that mean? So therefore, right, so I hope you got the idea, right? So there exists, what should I call it? U1, sorry, U0 to U M1 in S, right? So what does XY in R to the M1 mean? There exists U0 to UM1 in S such that X is equal to U0, UM1 is equal to Y, and UI minus 1 UI is in R for all R. And similarly, there exists V0 to VM2 in S such that what? Y is equal to V0, Vm2 is equal to Z, and Vi minus 1 Vi, Vj minus 1 Vj if you like, is in R for all G. Right, so this just by the definition of the relation R to the M1 and R to the M2. Right, so now what do we have? So therefore what? So therefore consider sequence. Consider the sequence X is equal to U0, U1, U2 to what? Up to UM1, which is equal to V0, and then you go up to VM2, right? So which is equal to Y, right? So every consecutive pair of elements in the sequence is in R. So therefore XY, right? So this is the path of length M1 plus M2, or rather walk of length M1 plus M2. So therefore XY belongs to the set R to the M1 plus M2. Right, so therefore XZ belongs to the set R to the M1 plus M2, sorry. And therefore XZ belongs to RHS. Right, so what did we prove? We proved that for every XY in RHS and YZ in RHS, the pair XZ must also belong to the RHS, which means RHS is a transitive relation. Okay, is everything clear up to this point? Okay, so now, right, so now as stated again, so this still doesn't give us an algorithm, right? Because if we were to kind of try to implement this property as an algorithm, you'll have to compute R to the power M for every M in the set of natural numbers. That doesn't make sense. Okay, so how do we get an algorithm now? Suppose S is a finite set. How do we get an algorithm now? We definitely don't want to compute R to the power M for every integer n. Can we just get away by computing R to the power M for some finitely many integers n?
The size of the set S.
Size of the set S. Nice. Nice. Okay. Yeah, Aniruddha, your hand was up, I think.
Yeah, same thing.
Same thing. Okay, cool. Cool. So now let us see what happens when S is a finite set. Let's call it size n, and then we'll see that R plus, right? So I don't need to write R plus as an infinite union. I can in fact write R plus as a finite union of powers of R, and therefore that makes that kind of gives us an algorithm to compute R plus. Cool. So let's do that. So let R be a relation on a set S. We had a finite set S of size n, then we claim that R plus is just the union over M going from 1 through N of what? Of R to the M. Right, so recall this R plus. I mean, we proved in the last slide that right. So we proved on the last slide that R plus is this infinite union. So it is equivalent to proving that so it's equivalent to prove that this infinite union that is union over all M in N R to the M is equal to union over M going from 1 through N R to the M. Right, so the plan of the proof is again the same. Let's call this LHS. Let's call this RHS. We will prove LHS is a subset of RHS, RHS is a subset of LHS, and that will do our job. Which direction is easy? Which direction is easy?
RHS is a subset of LHS.
Really. By definition. Yeah.
Sir, also we can say that RHS is a subset of the infinite union, so LHS is a subset of RHS, like that.
What? RHS is a subset of the infinite union, so what?
No.
Okay, so how do you prove LHS is a subset of RHS? Suppose.
Well, here, so shouldn't M be 0 to N?
Why?
So I mean, not necessarily 0, but if a relation x comma x exists in R, then how will we ensure it exists in R plus?
Because it will exist in R to the power 1, no?
Oh, okay, sir.
Yeah, what is R to the power 1? That is just R.
Okay, sir.
Okay, so suppose xy is in LHS. Right, so what does that mean? Okay, does somebody want to complete the proof? Right, so xy is in LHS, so therefore that means that there exists some integer m prime such that there exists some integer m, there exists some natural number n prime such that xy is in R to the m prime. Now what? Right, so if m prime itself is less than n, then we are done. Yes, Rishabh?
Yeah, if m prime is greater than n, there are two elements which are repeated in this path from x to y.
Yeah, so you have this x is equal to z0, z1 up to zm prime, which is equal to y. So then you are saying that sum 2 must be equal.
Yep. Okay. And you can just delete that portion. And you instead define m prime to be the smallest n in which xy lies.
Good. So now you are getting a hang of the well ordering principle, right? So how do you use it in an extremely clean manner? Very nice. Okay. Yeah, so we will do that. Arin?
Yeah, sir, I wanted to do this with paths. So in any graph, the maximum possible path length would be the number of vertices.
Okay.
Yes, sir. So and here, if we have path length greater than the number of vertices, then the resulting thing should be a walk.
Yeah. Okay.
And since there is a walk from x to y, there must be a path from x to y.
Okay, you could do that. Yeah, but that sounds like a good idea too. But let's do it extremely cleanly. So so there exists m prime such that xy is in R to the m prime. So which means the set. So that is, this means that the set m prime such that xy is in R to the m prime is not an empty set. Not the empty set. So therefore, so we are using well ordering principle over here, obviously. right? Let M be the smallest element of this set M prime such that xy is in R to the power M prime. Right. So now what? Now so therefore there exists a sequence Z0 Zm in what? In S such that x is Z0, Zm is y, and for all I, Zi minus 1 Zi is in the relation R. Now what do we have? So now right. So now what are distinct for let's be careful about it. So what can we say? Which of these Zi's are distinct necessarily? Can we say that all the Zi's are distinct?
No.
So what should we really say?
So like you can make two cases based on m is less than n, m is greater than n.
Okay.
And yeah, if m is less than n, you're done. Less than or equal to n, you're done. If m is greater than n, then you have there's two vertices that are repeated in Z1 to Zm.
But my problem is, what if Z0 is equal to Zm, and that is the only repeated thing? That is a slight thing to worry about, right? Because potentially x could be equal to y, no? Who stops you?
If you take that case separately, you're done because it's contained in R1.
Yeah, maybe you could do that way. So what I would rather do is right. So Z1 through Zm, I'll say are distinct. Else, contradiction to the definition of M. Right? If some Zi from Z1 through Zm, among Z1 through Zm, if some Zi is equal to Zj for I not equal to j, then you can get a smaller path from x to y. Okay, so that is just little corner case that we need to handle. Right. So now these are distinct. So therefore, what do you have? So therefore, M. Right. So because these are distinct elements of the set S, right? So therefore, M must be less than or equal to N. Right. So therefore, XY belongs to RHS.
Sir, what do we do when Z0 and Zm are same?
Sorry?
Sir, what do we do when Z0 and Zm are same?
We don't care, right? We are just worried about Z1 through Zm over here. And all we are saying is those are distinct.
Okay.
Okay. Yeah. By the way, I missed up something. So M is the smallest element of this set. So therefore, what do you mean? So what do you have? So therefore, XY must be in R to the M. Right. So that is one thing I forgot to write. Good. So now what? So now we have this R plus is equal to union over M equal to 1 through N of R to the power M, and that is now going to give you an algorithm. Right. So this gives an algorithm. Right. So what is the algorithm to compute? So maybe let's write on the next slide. Right. So recall. R plus is equal to union over M equal to 1 through N R to the M, where R is a relation on a set S of size N. Good. So now what is the algorithm? So right. So what do you do? So for right. To compute R plus given R. So what do you do? For M equal to 1 to N, compute R plus, and then just return the union over m equal to 1 through n R to the power n. Right. So one little idea that might be helpful in doing the first step is the following. So claim R to the power n is just the set of all xy for which there exists some z in S such that xz is in R to the power n, R to the power m, R to the power m minus 1, and zy is in R. Right. So what is R to the power m? R to the power m is the set of all xy for which there exists this kind of a length m walk. Right. And all we are saying is instead of finding all possible length m walks, what you could do is, suppose you have computed R to the power m minus 1 already. Right. So let's just find all possible xy such that for which there exists some z such that xz is in R to the m minus 1. So this is my z, xz is in R to the m minus 1, and zy is in R. Right. So I'll leave this for you to figure out. Raise your hand if you think you will not be able to prove this claim. Let's see. Yeah, you don't have to feel embarrassed, by the way. I mean, although I have said it's an easy claim, you don't have to feel embarrassed. It is easy to miss things that are taught in class. So that's extremely, it's completely fine if you say that you will not be able to prove this claim on your own. Yeah, so just be frank about it. Okay, so apparently the claim seems to be easy for the class. So I'll leave this left as exercise. Right. So now there is a nice matrix interpretation to this computation. Right. So this is so having right. So in this loop for m equal to go in 1 through n, you are computing compute R to the power m. No, R to the power m. Yeah, you are computing R to the power m. Right. So you have already computed R to the power m minus 1 in the previous iteration of the loop. You already have R at your disposal. So you can just compute this in a reasonable amount of time. Aniruddha?
So I had a question regarding a possible relation between R power m and R power n. So if we say that R power m is equal to R power m plus 1, can we say that, so suppose something like a stationary state, if we find that R power m is equal to R power m plus 1, can we say that that would extend till infinity? So R power m equals R power m plus 1 equals R power m plus 2 equals, and so on and so forth.
Okay, let me state your claim. So your claim seems to be that if R power m is equal to R power m plus 1, then what did you say? Then these are also equal to R to the power m plus 1 is equal to R to the power m plus 2. Let me just state it that way, and then that will extend. If this is true, then it will extend. No, is that true?
No, not R. Then R power m is equal to R power n for all n greater than m.
But that's what I've said, right? Even if I just say this, that is equivalent to what you said, no?
Okay, yeah.
Right, because R to the power m plus 1 is R to the power m plus 2. Assuming this claim is true, R to the power m plus 2 will be equal to R to the power m plus 3, and so on. Is this claim true? Right. So now suppose there is a right. So
Sir, such a claim would be true only if R is like X is joint, like if it is just XX. Right?
Sorry?
Such a claim, for such a claim to be true, you'll have the relation R to be XX, like just the smallest reflexive relation.
Not necessarily, right? Another example is where R is just S cross S. Right. Okay. By the way, this claim is true if this claim is clearly true if R is reflexive, I believe. Right. So this is true, certainly true if R is reflexive. What if R is not reflexive? Can we say that? I am doubtful, because let's try to construct an example, right? Let's say you have X is related to Y, Y is related to X, so which means XX. Wait, no, acha. So you are saying R to the power M is equal to R to the power M plus 1. Yeah, I think I'll have to think. I don't have an immediate proof, or unless.
If this claim is true, what it means is that if we find like a stationary state of R, then we only need to compute up till that point. We don't need to, like, minimum of N and M. We will need to compute up till that.
That makes sense. That absolutely makes sense. But yeah, actually, what?
Yes.
So what it should, okay, so basically the claim you should make should not be about R power M. It should really be union over J going from 1 through M, R power M, R power J. If this is equal to union over J equal to 1 through M plus 1 R power J, then they are equal to R plus. I believe this is certainly true.
Okay.
Right. So basically, instead of finding each Ri and then finally taking the union, every time you are finding some R to the power M and taking its union with whatever you have done so far. And if you find that in a particular iteration, well, you have not changed anything due to computing this union, then you can just stop over there. Yeah, Aniruddha?
No, that's it.
Okay, fine. Yeah, but let's not worry about these improvements for now. Let's leave them possibly to the tutorial or maybe the homework. Right. Okay. So yeah, so the one interpretation of this algorithm which I wanted you to think of is the following, right? So let us represent this R. Let us represent any relation by a matrix, right? So how do we represent a relation R prime over the set S as a matrix? Right. So there is a natural way of doing that. Right. So we can think of a n cross n matrix, where the rows are indexed by the set S, the columns are indexed by the set S, right? And then your xyth entry in this matrix is 1 if this entry is 1 if xy belongs to R prime and 0 otherwise. Okay. So now let us say you have this matrix which represents R to the power M minus 1 and this matrix which represents R. Right. So how are you computing the matrix representation of R to the power M? Can you vaguely see a relation with some matrix operation that you have studied earlier? Right. So this is a matrix representation of R to the power M minus 1. This is a matrix relation of R. And how do we find the matrix representation of R to the power M? Right. So what is the xyth entry of this? Right. So xyth entry over here is really, right, as per this claim, is really 1 if there exists Z such that there exists Z such that what? There exists Z such that the xzth entry of this matrix is 1 and the zyth entry of this matrix is 1. Yeah, Rishabh?
So what you do is like have matrix multiplication, but you replace your number of multiplication of numbers with an and the sum with an OR.
Nice.
Yeah, that works.
Nice, right? So what you're doing over here is to find the xyth entry, you're looking at the xth row over here and the yth column. And now you are asking the question, does there exist a Z such that the zth entry in this row and the yth entry in this column are both 1. Right, so basically instead of multiplying entries over here, first entry with the first entry and so on, you are ANDing the entries, and then you're taking the OR of this entire vector of Boolean values that you'll get. Right, so this is nothing but matrix multiplication, except that instead of except that firstly you're multiplying two Boolean matrices or whatever. We should probably not call it multiplication, right? But okay, you're operating on some two Boolean matrices where multiplication is getting replaced by and addition is getting replaced by or. Good. So which means yeah. So I believe this. Yeah, I think this is a good point to leave. Right. So let's not even. Let's not try to simplify this any further. Yeah. So basically, what I'm trying to say is this r to the power m. Having computed r to the power m minus 1, this computation can be done in like order n cube time. Right. Matrix multiplication, or I mean, there are faster algorithms to do matrix multiplication, but probably they'll not extend to this modified setup where multiplication becomes and addition becomes or. But certainly in order n cube time you can do this, and then finally you have to repeat this loop order n times. So basically your overall running time will become something like order n to the 4. Rishabh?
Yeah, about like you could reduce it to matrix multiplication. You could just do a normal matrix multiplication, and then at the end, if and for all the entries which have a non-zero value, replace it with a 1.
Really? Can you do that?
Yeah, because
I was
because both sides are positive, so it's not. So if at some point will be non-zero, you could like. It will always be non-zero.
I see. So all acha. So basically you're trying to say that, okay, look, these are 0 1 matrices, just multiply them as you would multiply in a usual manner, and then just replace the positive entries with a 1 and leave the zeros alone. Okay, yeah. Makes sense. So probably even faster.
So does this also mean that, for example, if we don't make anything 0 1, so r to the power m means that each entry is the number of m length paths or m length walks from one place to another?
Yes, very nice observation. Very nice observation. Try to prove it formally by induction. Yes. Right. So I did introduce the notion of an adjacency matrix of a graph, but yeah, that's what you are hinting at. Yes.
I still think the bitwise one would be faster because you can just take bits and a bitwise and then ORing all the bits would possibly be faster.
But that's definitely going to take order n cube time, right?
No, because you'll be doing it row wise, and if you take 2 rows of the same, I'm assuming bitwise and is like a O1 operation, and same with the OR. Basically, you just need one.
Of a vector is O1 operation. Acha, that's what you are assuming. Okay. Yeah. Depending on your assumption, then this could potentially become faster. Yes. Yeah. I'm just assuming that you can, in a unit amount of time, you can just manipulate a constant number of bits. Okay, so which is why I said order n cubed. Okay, fine, cool. Yeah, how much time do we have? 9 more minutes. Cool. Okay, we finished a bit earlier than what I had expected. Okay, fine. So now, okay, so here are some claims for you to try on your own. Right. So now the question we'll try to answer is, so this gives us how to compute a transitive closure. Suppose I want to compute Suppose I want to compute a reflexive transitive closure. What do I do? What should we replace this by?
Sir, it would be same. We should not replace it by anything.
But I want a reflexive transitive closure.
Okay. I should add 0, m equal to 0.
M equal to 0 to whatever. Yeah. Right. So check. So claim the reflexive transitive closure of R is union over M in N union 0 of R to the N, right? So this is the difference, right? So that 0 is going to ensure that your relation is reflexive, right? And idea is the same. LHS subset of RHS, RHS subset of LHS, right? So you will prove that LHS subset of RHS should be easy. And you will prove that RHS in fact is a reflexive transitive relation over here. So therefore it must be a subset of LHS. I'll leave for this you to figure out. Claim. Right. So now my question is, suppose you want to find the reflexive symmetric transitive closure of a relation. What do? What out of these three properties, which one should you ensure first, and then ensure the other two properties? Does it matter first of all?
Symmetricity.
Yeah, Arvind.
Symmetricity. If we make some superset, if we make the smallest superset symmetric, the smallest symmetric superset of R, then we would do the same algorithm as in reflexive transitive closure, and we would get. So we should ensure symmetricity first.
You should ensure symmetricity first, and then you take the reflexive transitive closure. Cool. So my claim next is going to be if R is symmetric, then for all n in capital N union 0, R to the power n is also symmetric. Right, and then therefore in order to compute the reflexive symmetric transitive closure, so how do you compute it? Oh, by the way, I should have, sorry, there is something important that I missed. I should have said that, right, so similarly, claim, right, so what happens in the finite case, right, so the reflexive transitive closure of R is union over M equal to 0 to N R to the M if size of S is equal to N, right? So obviously I'm not stating the same thing over and over again. R is some relation defined on the finite set S of size M, N. Then I claim that the reflexive transitive closure is just this finite union. Rishabh?
Yeah, so we are taking the finite case separately. So is the first claim true for infinite sets?
This one?
Yeah.
What is your concern? I don't understand.
Like, is it true for infinite sets?
You agree that the earlier claim was true for infinite sets, right? I mean, if I just try to find the transitive closure.
Yeah, so like even the transitive closure one, is it true for infinite sets?
Yeah, of course. That's what we proved, no? Where did we, right, so this claim, where did we assume that S is a finite set? We never assumed that S is a finite set. So let me just remark that S is not necessarily finite.
So the algorithm assumes to be finite.
The algorithm assumes to be finite. Yes. But this theorem doesn't assume S is a finite set. Right. So this theorem holds for all sets S, and this theorem holds for finite sets. And this theorem can be converted into an algorithm. So similarly, if you are trying to find the reflexive transitive closure, here again S is not necessarily finite. And the second claim holds when S is a finite set, right? So when S is a finite set, all we are saying is you don't really need to compute the infinite union, right? Is it okay now?
Yeah.
Yeah. By the way, I think it should be possible to reduce this n to n minus 1. Just check. I believe it should be the case, right? So basically, the only reason you needed an n over here is the case where x is equal to y in this proof, right? That is the only case where you needed this n, right? Where you needed to take the union with r to the n. But if r to the 0 itself is going to ensure that, then you don't need this n, I believe. Just check. Yeah. So right. So let me just state it as a question. I haven't checked this myself. Is this equal to union over m equal to 0 to n minus 1 of r to the n? Just check. Okay, yeah, coming back to how do you compute the reflexive transitive closure? First step is make relation reflexive. Make relation symmetric by adding all xy such that yx is in R and xy is not in R. Right, so make the relation symmetric and then take the reflexive transitive closure. Right, and then this property, this claim is going to ensure that all the powers of the relation that you compute are going to be symmetric, and then finally when you take the union of all those, that is also going to be symmetric. Okay, any questions? We have just less than a minute left. Okay, fine. So if there are no questions, oh yeah, by the way, tutorial, should we have it today in the evening or should we have it on Saturday? Let's take a quick poll. How many of you prefer today? Raise your hands quickly. Today over Saturday. Okay, Arun prefers to have it today over Saturday. Raise your hand if you prefer to have it on Saturday over today, so that you get some more time to try out. Okay, fine. So there is much more, many more votes in favor of Saturday. So let's have the tutorial on Saturday. Usual time 6:30 to 7:30 in the evening. Sounds good. All right, chalo. See you on Saturday in the lecture 9:30 AM.